So welcome to everybody. What you see here is the 8th week lecture of the drive techniques. And last week we were talking about energy storage, basically different kind of batteries and also a bit of fuel cells. So everything for storing electrical energy under any form. And this week we will continue with the engines themselves. So I will try to explain you really in a nutshell the characteristics and behavior of different type of electrical engine. I don't know if you have learned about it in your previous studies in high school or in BSc or MSc, electric engines? Not yet? Yeah. Some basics. Okay. DC motors. Okay. So I prefer to restart from the zero, or roughly from the basics, in order to explain things. So, electrical engines. Electric engines. Here I will talk only about rotating machinery, so I will not talk about transformers and other static electric engines, just the rotating things that are used to drive a vehicle, usually. So the first thing to know is the principle of induction. Induction. What does it mean, induction, here? Induction is a phenomenon observed, let's say, 150 years ago, roughly. And the induction, and the description is related to two scientists. Maybe you have heard about, or at least you know their name. The first guy is Faraday, who was an English scientist dealing with electricity. And the second guy is Ørsted. Ørsted was a Danish guy in the same time. They lived in the late 19th century. And the observation they made were the following. Ørsted, he was playing with a wire, metallic wire. He put electricity in, and he put a compass next to the electric wire. And he was curious to see if the electricity has any magnetic effect. And he was switching on the electricity. Nothing happened with the compass needle. Waited a bit, waited long. Nothing happened. Then he switched off electricity. That time, remember, that time they had just batteries, simple batteries like carbon discs and textile disc with acid and other nickel or other metal discs. So they were just continuous current energy sources. And then after a certain time, Ørsted noted that the compass needle does move, but only if he switches the current, either on or off. When the current is going in the metallic wire, then nothing happens with the compass. What about Faraday? Faraday, he was playing with magnets, because this time the electric magnets were a very trendy topic. And he was surprised to see that if he's playing with his magnets and he's moving his magnets and there's a wire around, then electricity is created somehow in the metallic wire. So the two observations were quite soon joined. And we can say that if if current flows in a wire, a magnetic field is created around, and this magnetic field is more or less proportional with the current inside, also with variation, whatever. And the opposite, if a magnetic field changes around a conductive wire, electric current is created inside, or generated, maybe it's better. It's generated. Okay? These are the basic things that drive the electric engines. That time, scientists were playing a lot with electric magnets. For example, the American Henry, he was an expert in electric magnets, and that's because it was quite easy to make linear motion with these electric magnets. And remember, these times, the 19th century was the century of the steam engines, huge pistons, huge flywheels, spectacular slow alternating motion of the parts, and the electric magnets were quite easy to use for creating alternating motion. But the basic idea was to use the electricity directly for making rotative motion without putting the alternative motion in the middle of the system. And there was a further observation that helped to create the clean electric rotating machine. And this was the observation of Lorenz, or what we call the Lorenz, capital L, no, Lorenz Force. The Lorenz Force is based on the following observation. If you get a homogeneous magnetic field created somehow, let's say you get here the north pole of a magnet, and here you get the south pole of a magnet, and you get a more or less homogeneous magnetic field. Here you get the magnetic lines between the north and south poles. And if you put in this zone a wire, let's have the wire in this yellow color. So you put a wire here, a loop, wire loop. You will you will see interesting things. If you put or if you apply a continuous current to this wire loop put in a magnetic field, you will see that the magnetic field wants to turn this loop. It wants to turn so to having a parallel position with magnetic lines. Okay? This was a quite interesting observation I just noted. So Lorenz Force, let's have a homogeneous magnetic field. Let's have a wire loop inside the field. Then we say, let's apply current to the loop. And if you put current to the loop, then you will see, based on Faraday and Ørsted's works, that a small, or just not a small, just a magnetic field will be created around the loop, and the strength of the field will be proportional with the intensity of the current. And what happens if the plane of the wire is perpendicular to the homogeneous field direction? If plane of the loop is perpendicular to the plane of the field, so you get, this is the plane of the field, and you get the loop, the wire loop, which is perpendicular to the plane of the field. What happens? A rotating torque wants to turn the loop. And is it working till the infinity? Not really. The turning is active till the loop goes parallel with the magnetic lines. Okay, and that's it. After it remains calm without problem. Till reaching a parallel position. With the field. Okay? And this is a very important observation. It was made maybe by the physician Lorenz. So if you put a wire and you put current in the wire loop, the magnetic field will turn it. And from this observation, there's just one jump. Or here, one more remark. Just one remark here. Remark. Strengths of the turning force it's proportional with the current. It's proportional with the magnetic field intensity. And orientation of turning. If it turns left or right, this depends on orientation of current. So the polarity, if you like, polarity of the current joined to the applied to the wire loop. Okay? I think you have learned these things in secondary school or in university. And how we build an electric engine based on that. The story says that the first guy to make rotating machines based on these principles, there were two guys. The first guy was a Hungarian teacher who wanted to illustrate the effect. He wanted to make a demonstration tool for the students. And he was a guy called Jedlik. Ányos. Jedlik. He was a priest, a Catholic priest, and he was teaching at the Catholic high school of Pannonhalma in Hungary. And he was a guy who made a lot of experiments, a lot of demonstrative small tools. He had a lot of inventions, but he was a simple priest. He was not interested in making any business. He just showed the guys, students, what are the physical phenomena and how they are working. In the same time, in Germany, there was a guy called Siemens, Werner Siemens. And as the electricity was very, very, very trendy that time, as we get these days, Siemens also, he made experiments for making a rotative machine based on electricity. And Siemens, some weeks or some months later, had the similar idea and made a rotating machine based on the same idea. But as Siemens was a businessman and not a teacher, he made the patents and whatever was necessary for making electric engines. Okay, so I have to add the name of Werner Siemens. if you know the name Siemens, now it's a big company. Now it's a big company, but he started. You've got names like Tesla, you've got names like Edison, you've got names like Bosch and Siemens, and these names are starting with small backyard workshops and basic physical experiments. Okay. Typically, like you get Apple, for example, or Microsoft, but a century later, the same phenomenon. Okay, so now some words about the layout of electric engines. What are the basic parts they are composed of? Every electric engine is based on the Lorenz Force principle. So you put a magnet, or you put a wire loop. You apply current to the wire loop, and you create somehow a homogeneous magnetic field around, so you get instantly the rotative motion. So layout, 1, 2, 3, layout. Layout of electric engines. So you get a stator part. Usually the stator part is the part that is not moving. Okay. The not moving part is responsible for creating the electric field. Task. Sorry, magnetic field. Creating magnetic field. How do we create magnetic field? Either we use magnets, natural magnets, or, which is more common, or we use electromagnets. How an electromagnet looks like. An electromagnet has got a coil, a wire coil of wire that creates a magnetic field when a current is applied to the coil. And so that this magnetic field could be strong enough and could formulate or form a homogeneous field, you get a steel, what's the English word for that? No, maybe a steel core, a steel material around which the winding or the coil is made. And the task of the steel core is to keep the magnetic field inside. Okay, to be a conductivity for the magnetic field. So it's not a very hard and very strong type of steel, no. It's a quite soft steel which has special magnetic properties, namely very little resistance to magnetic force. Okay? So in the stator, usually we find electromagnets that are composed of a wire coil and a steel core. And they are usually built by pairs. So north and south side of the magnetic field. Okay? Is it clear like this? Okay. And the rotor is the moving part. Rotor, the moving part. The rotor is the thing that contains the wire loop, the yellow one that was turning in the magnetic field. Okay. It contains the moving, namely rotating wire loop. And here, the first problem is that if you got just one wire loop, you put it perpendicularly to the magnetic field, and the magnetic field starts to turn it. Once it arrived to the parallel position, it doesn't want to move anymore. So for having a constant torque that's applied to the rotor, what do? We use more than one loop. We use a high number of loops. So to keep moving the system. Okay? This is the idea of Jedlik and also the idea of Siemens. To keep continuous motion, there are a series of loops. Or there is, sorry for my English. There is a series of loops. How many? It depends on the construction of the rotor. Let's say hundreds or thousands, it depends. So, usually we call it windings. It's the sum of the coils present on the system. And again, here you get a steel core, again, to help the establishment of the magnetic field in the rotor. Okay, so note that the electric engine is basically working upon the interaction between two magnetic fields. And the principle is that one magnetic field is fixed, and the second magnetic field is moving. Okay, this is the core of the thing. How we create magnetic field, either by electricity or by natural magnets, both can happen. But this is the important. This is the core. Okay. Okay. So like this, we will have at least one loop will still be perpendicular to the field, to the magnetic field. Okay, so at least one loop will still be perpendicular to the magnetic field, so we will have a continuous motion of the rotor. How we put the electricity inside the wire loop? This is a quite important question. It was not obvious because it's a moving thing. So we have to make a connection between a moving part and the electricity, source of electricity. So how to put current into the rotor? This was a basic question. And for that, we have the following solution. The wire loop ends are braced to a part called the commutator. The commutator is like a cake. Okay? Commutator is like a cake. You get the slides of cakes, as in a, what's the name is? Sweet shop. You can buy either complete round cakes or you can buy slices. And often, if you can buy slices, you get the prefabricated slices. And you get a kind of plastic insulating screen between the slice in order to keep the shape. We remember? Have you seen such things? This is exactly how a commutator looks like. Exactly. So for example, you get the slices like this. Like a cake. Slice. They are flat metal parts, and between them, what do you have? Exactly. You get insulation layers, again, smooth insulating bars, or not bars, flat sheets. And basically, they look like a round circular circumference. Okay? And the ends of the wire are soldered to these metallic parts. Okay? So you've got two outputs of each wire loop on one end, and you get also the output on the other end. So this part of the thing is clear. You get the insulation between. And how you put the current in. You put the current in using carbon brushes. Carbon brush is nothing else than a piece of pure carbon. This is a carbon brush here. And the second one is below, let's hope. The second carbon brush and the first carbon brush are linked to the power source, source of electricity. Okay? The carbon is a quite good, no, the carbon can transmit the electricity, and through its surface, it transmits the electricity to a certain number of wires. Not to just one wire loop, but let's say to 4, 5, 6, depending on the width and depending on the diameter of the commutator. Okay? And when the commutator turns a bit, the brush, I call it carbon brush. The brush remains on position and the commutator turns below. So if it turns like this, Then a new loop enters between the brushes, so gets the electricity, and the previous one leaves the brushes and leaves the electricity. It becomes non-active. Okay? This is how it works. So we can say this is a wire and metal sheet. And the green was insulating sheet. Okay? Maybe you have learned this. And the position of the brushes is such that there are always the loops that are in perpendicular to the magnetic field that can obtain the electricity. Okay? So these are the inventions of Siemens and Jedlik. So here you get one end of the current, and here you get a second end of the current. U intensity, and here you get the Earth. Okay? Is it complicated? No. Nothing is complicated unless we start to do it. No. So this is what I wanted to tell in a nutshell about the principle of how an electrical engine works. So again, it works upon the reaction of two magnetic fields. And one magnetic field can move relatively to the other. And we've got to create somehow both the static field and the moving field. And the classification of the electric engines usually is based on how we create the static field and how we create the moving field. Okay? This is the base, shortly. Now, so now let's go to see the classification of electric engines. Obviously, the electric engineers learn this using vectors and matrices and cross products and so on. The principle is the same, just the mathematics is much more nice. Okay, so classification of electric motors. Is based on two parameters. What makes the electric fields, the magnetic fields. First point of view, And the second is which type of current is the source of energy. Okay, these are the two things. Okay? Now, let's see for first the continuous current motors. Continuous. Okay? These are the CC motors. Do you know what is a continuous current? How it looks like? Sorry? Continuous current means that the tension or current in the time, let's see the tension, it's easier, tension U, it has constant value in time. If it's 12 volt, then it remains 12 volt regardless the variation of time. Okay? You get a battery of a given tension, or you get a grid, a network for given tension. In Budapest, for the tramways, we get 600 volts continuous current, which is constant in time, 600 volt of tension. We got 900 volt for the suburban railways, the HAVE, and we get alternative current for the normal railway. So 3 types of grid network, of grid tension. So, but here, most important is the continuous current. Historically, these were the first engines to be created, because we could make electric batteries providing continuous current by chemical way really easily. Let's see the presentation or the symbolic representation. The symbolic representation will be the following. You will get a rotor, you will get a brush, not only one, a pair of brushes, and you will get a coil to provide the constant magnetic field. Okay? Symbolic representation, so here you get the stator coil. Here you get what you get here. You get the rotor, and this is a brush. And I haven't drawn the wires linking the stator and rotor. Okay? And here in a continuous current motor, we get the important remark. Both magnetic fields both magnetic fields are created by a current. So you've got electric magnets both in stator and in rotor. Okay? So you've got wire coils both in the stator and in the rotor. Very nice red or yellow-red, copper-looking coils. Now, could you copy it? Okay. Types of circuit. Types of circuit for the continuous current motors. I will use the symbolic representation I've just presented. We will have 4 of these. The first, so I will draw 4 symbols. This is the motor here. Second symbol. Third symbol. And fourth symbol. Okay. And now I will draw the wires. I will draw the wires. How will I do it? I will draw always one brush I will link to the earth. If you have learned electricity in high school, you know that this is the earth, one pole of the system. And the other end goes in somewhere here. This is where the plus goes in the system, okay? The U. U tension is here. Okay? And now the types of circuit you can use. Excitement in series. Okay? When you get the stator and rotor linked in a serial circuit. Serial excitation. This is here branched in series. The second type of circuit is when you get a parallel excitation. Okay, do you see? Parallel excitation. And the number 3 is a bit more complicated. I will try to make a bit of drawing. So here you get a part of the coil that goes in parallel. And you've got a second part of the coil that goes in series with the rotor. And this is what you call a mixed excitation. when the stator is split in two half coils. One half coil is parallel and the other half coil is serially wired in the system. Okay? And the fourth possibility is what we call the external excitation, when we get an exciting tension and we get a working tension. We get two sources of tension, two sources of current. The exciting current, exciting tension, plus the tension for the rotor, and they are quite different. Nothing links them practically, just the magnetic fields. Okay? That's what we call the external excitation. Okay? Is it clear? The four types? Okay. What do we use from these things the most often? We use the serial excitation and we use the parallel excitation. These are the most often used. The external excitation is mostly for energy production, so it's not used as motor. Mixed excitation, it's quite complicated. We prefer not to use this in motors. Okay? So now let's have some words about the torque curves of the serial and parallel excitation curves. Sorry, serial and parallel excited electric motors. Let's have a classic RPM versus torque curve. Here we get N being, let's say, RPM, rotation per minute. And here you get the torque in Newton meters, or you get the drag force in newtons. It depends how you like. And we get the following curves. For a serially excited motor, we get a curve looking like this. This is what we have in serial excitation. And we have a curve like this for parallel or mixed excitation. Okay? These are the typical shapes of torque versus RPM curves. Okay? What do you see on these curves? On the yellow one, the serial excitation curve, you see that when the RPM decreases towards 0, the torque increases. And this increase is not linear, it's quite exponential one. And you see the curve that if you are close to 0 RPM, the torque seems to go till infinite. What you see for the parallel case, you see that you get a mean RPM in the system. And if your load is decreasing, the RPM changes very little. And in the opposite direction, if the load is increasing, even in this case, the RPM changes very little. Okay. By the setting of the winding and electric motor parameters, you can set the slope of the line. It's practically a line. While the serial extension curve is more a hyperbole, and here also you can set it or tune it, the shape, but it's more or less a hyperbole. Which one is more suitable for vehicles? If you know, if you can use a bike, a simple bike, with your pedals, you know that how, when it is difficult to ride a bike. When it's high slope, but before that, starting. Exactly. You've got to push hard a bike, or the pedal of the bike, when you want to start. Once you went away, you got a more or less constant speed. It's much easier to push with the pedals, to press on the pedals. Okay? So for a vehicle, roughly, we require a high torque around 0 RPM to start, to launch the vehicle. And once it's in motion, we've got just to keep the state of motion, and that can be done with a relatively small quantity of torque. Okay? So it seems that this circular excitation machine is quite ideal for driving vehicles. What about the parallel or mixed excitation machine? We see that it has a property of keeping the RPM mostly independently of the load. So this one we prefer to use in specific purposes when the load is changing quite in a wide range. Namely, for example, machine tools, lathes, milling machines. When either you apply the knife on the material or you remove it, the load changes quite importantly. Or you get cranes or elevators. Okay, we get this one. Vehicles, we get more this one. And us, no. I'm speaking too much, as usually. We have to write down some basic sentences. So, observations. That we see from here is that serially excited CC engine gives torque at large RPM domain. And also we see that problem of RPM rise at low load why an RPM rise can be a problem in a serially excited CC engines? That's just because of the commutator. Because you know, with revolution we get a centrifugal force, that wants to move the objects towards the radius of the cylinder in which the thing is rotating. And below, or above a certain speed, the commutator's parts tend to go in radial direction, and the commutator can explode. Okay? And not only explode, but also you have seen that in the commutator you get a certain level radius for the top of the wire sheets, and you get one level below for the insulating sheets, if you were observing the sketch. So sheet, gap, sheet, gap, sheet, gap, sheet, gap for the wires. And this thing acts as a small circular saw on the surface of the brush. Okay? So small little wedges, they are just abrasing or removing a thin layer from the surface of the brush. So a commutator brush system is always sensitive to the RPMs. It goes quite well at low RPMs, but above a certain RPM limit, it can explode, and the wear of the brushes is really accelerated. And also it's noisy, and whatever you imagine. Okay? So let's say optimal. It's optimal. Oh, no. Again. It's optimal for vehicles that are heavy. Why I say they are heavy? That's they can resist to the high starting torque. The motor cannot spin up fast. Okay. By the time it starts to spin quickly, the vehicle has started to move, so there's no so huge torque. So it keeps the RPM at a sufficiently low level. And parallelly excited CC engine. Continuous current excited. Yeah. Here we get it gives a parallelly excited CC engine. It gives torque in a narrow RPM domain. And RPM is kept constant regardless the load. So this is optimal for tools and lifting machines. Machine tools. Cranes, elevators. Okay. Is it clear? So the first tramways and the first trolleybuses were using a continuous current serially excited engine. in Europe here. We got our tramway, the 4 and 6 tramway in Budapest, line 4 and 6. This was built in 1876 or 1886, so more than 140 years ago. And since then, they are using this continuous current system. The first wagons were using a Siemens engine and Siemens technology. And even today, they are using Siemens technology, as I see, even the modern ones. Wait a bit, yeah. The engines are not continuous current engines anymore, let's say since the last 10 years, but before it was exclusively continuous current. And the grid tension is still 600 volts continuous current. Okay? Yeah. So, to sum up shortly, properties. No. Yeah. It's difficult to write and talk in the same time. Properties of the continuous current engines. Yeah, in English they call also direct current engine, DC engines. Advantage, simple layout. Easy to control. Simple layout means you get a lot of copper wires inside, both in the stator for the homogeneous magnetic field and also in the rotor for the rotating wire loops. But you can do it without problem. You use special soft steel material for conducting the magnetic field, both in rotors and stator. And the control is the easiest possible. You get a series of resistances. If you put big resistance to the system, you get big current, strong current, big torque. If you put smaller resistance, you get smaller current, smaller torque, higher RPM. And that's all. You've got quite all the suburban railways, HAVEs in Budapest. And you can hear next to the driver's post when the when the wagon starts, that you hear clack, 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 when the magnetic contactors of the resistances are switching on or off and starting the electric engine. That's characteristic, clack, 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 soft magnetic noise. You can hear it. And the old tramways we had, they also had this key, let's say, there was a board for the magnetic contactors in the wagon. And when I was a student, and we had not flash drives but magnetic disks, we had to take care when we were traveling using tramways and suburban railways, because these magnetic contactors had their own magnetic field. And if it had an interaction with our floppy disks, it could easily format and rewrite our data. Oh, it was a long time, let's say 20 years ago, but still. It was a basic phenomenon when you were coming by tramway, you were standing with your floppy disks next to the bad end of the tramway when you had the magnetic contactors, And at home you were saving your data, and here you were putting your floppy disk inside the reader, and it was saying syntax error, fatal error, any kind of error possible. It does happen. It does happen sometimes. But if they are looked after and the normal maintenance is provided to these machines, they last, let's say, forever. They are heavy and noisy, but till you change regularly the brushes and you clean regularly the commutators, they last forever. Another disadvantage, for sure. You get the commutator. So you get RPM limit. You cannot spin the rotor too high because the commutator will explode. It's also noisy because you get a high frequency noise because the wire and sheets are entering and leaving the brush surface. It's like a continuous abrasion noise. And what else? The wear. Wear of what? The wear of every part composed in the commutator. You remember you got small gaps between the steel plates and the insulating plates. The insulating plates are less tall. That's for providing a sure contact between brush and conducting wire. But it has also the consequence that when you are cutting the small layers from the carbon brush, the carbon powder is accumulating in these gaps. And soon it makes conduction between the neighbor wire ends. And once you get longer and longer conduction between wire ends, it will short circuit your rotor. And it will decrease the power of your rotor because a lot of non-perpendicular wire loops will be under current at the same time. And in the wagons, when your carbon brush weighs 5 kilograms and you get 1/2 to 1 kilogram of carbon powder on your commutator, it can make fire. It can make a fantastic annular spark system that just electrically burns away your commutator wires, commutator sheets. So the wear is an important problem. And time by time, you've got to stop the machine, check the commutator, clean up the insulating gap, and regularly change the brush, and regularly remanufacture the circularity of the commutator part. So you have a lot of manutention problems or manutention tasks with the motor itself. And the second thing is the control by resistance. If you use resistance to control the engine in a tramway, that stops quite often and starts quite often. While it's starting and stopping, the current goes through resistances. And what the resistances are doing, mostly, they are making heat. So the efficiency of the control is quite low in such case. In winter, you are happy because it's heating up the wagon inside, but in summer also, and it's much comfortable in summer. If you get our old Russian metros in Budapest, In summer, you get the gap between the perron and the wagon. And once the wagon is arriving to the station and slowing down from high speed, you get a lot of heat coming up from the gap between the perron and the wagon. I don't know if you have observed this, but with the old Russian metros, it's quite often. So efficiency. Okay. Is it clear? So for simple purposes, or for cases when it starts to turn and we don't have to stop it too often, the continuous current machine is perfect. It's really perfect. In other case, when we want a fine control of the thing, or we want a good efficiency, or we want a close to zero manutention need, these days it's not the best solution.
So for the second disadvantage controlled by resistance,
Yeah.
It's less efficiency because of the generation of the heat.
Exactly. So the question was that here the problem is the efficiency, yeah, because the resistance makes heat. So the power is lost for making the heat. If we use other types of control device, using transistors or anything else, we get a much better efficiency for the system. But it's really easy to explain you. I have the example of charging an electric vehicle. It's battery charging, but relative to efficiency. If you charge an electric vehicle, you plug the end of the wire on the socket, and in a normal battery electric vehicle, in a car, let's say you get 14 amperes that is taken out of the socket, of the wall. In the car, what the battery sees is a charging of 7 amperes. 50%. Where is this 50%? For sure you get an inverter or a rectifier that makes continuous current for the battery from the tension of the alternative tension of the wall socket, for sure. But also you need to compensate the load of different cells in the battery, and you use resistances for that. So even at this point, resistance, you've got to have it somehow. But don't have it too big. And in a vehicle size, you get, for a wagon, a metro wagon, you get 250 kilograms of resistance. So it's the ceramic body plus the wire, but still, it's quarter ton, just resistance, just for making the control or the braking. So, and it provides heat, for sure. You remember, it's current square times resistance is the power of the heating. These days we are happy with the environment protection and other issues that seems to be more and more important. And the basic saying is that the best way to economize energy is to not to consume at all. Because if you don't need so much energy, you don't need to produce so much energy. And losses are everywhere, in the power plant, in solar plants, in the grid network, in your given device, everywhere. So if you don't have to produce, that's where you can save the most. There are tricky things like this. So even if an electric engine has got a good efficiency as engine itself, you've got the battery. the current transformation from the network to the battery. You get the control. And if you add the production of the electricity plus the network efficiency, you are not maybe at a so high overall efficiency level. Locally, for sure, you don't have the internal combustion engine emitting a lot of exhaust gases, for sure. But if you compare to the petrol production, internal combustion engine production, internal combustion engine efficiency, and you make the computations for a lifetime of 5 to 10 years, you don't have a huge difference in overall efficiency. So it's very important to see the things in system. For the press, for the advertising, it's very good to point out, this has a huge efficiency, a very good thing, okay. You know that in your sandwich, I don't know, the salami is very good. But also you get the paprika, you get the butter, you get the bread. And the sandwich is composed of all of these, and not just your salami. Remember these things. Okay, I think I stop it for now, for today. And next week we continue with the alternative current engines. Okay? Do you have any question regarding this? No? Then thank you for coming and see you next week. I'm afraid next week we'll have also a test in the evening, because we get always test at the second, after each second presentation. Okay? So thank you for coming and see you next week.